Yeah, this time I'm trying to record on, let's see, both of my computer here. Did I recording? Let's see. Okay, yeah, because I have the feeling that like my computer may overheat and hang because it's the for some reason the fan is keep running and a sec. I don't know why I cannot. Okay, I guess that's fine. So okay, can you guys give me some kind of like feedback like that my mic is working well? Okay,
Yes.
thanks. Yes. Okay, I guess the first thing I'm trying to do is I actually delay it for a long time now. So I just want to have like a couple of filters that I like to mention that actually is supposed to be in the slide since I several lectures before, but it delayed a little bit. And I like to mention that because I'm going to talk about actually the major topic we like to talk about is resampling, and we'll use Gaussian filter. So therefore, at least I should mention about that. So so this is the Gaussian filter. The first one I like to talk about Gaussian filter. So you have the filter response, impulse response is like this. So you have a peak like somewhere in the middle, of course, right? And then you decay. There's voice in the background. Is that I'm not sure. I'm pretty close to the mic already. I'm not sure. Maybe it's the fan, because that's what I'm saying. Like, yeah, I'm saying that like I have the feeling that like my computer may hang anytime because like whenever I overheat, it just hang. Okay. So yeah, but the fan is running. You just have a really good ear actually. So and yeah, we have the Gaussian filters like this. You see, like it's slowly decay like this one here, and it's just a Gaussian kernel. If you know like the Gaussian distribution, and this is exactly the Gaussian distribution here. So we have this specify the sigma, just specify like the variance. Sigma square is the variance, or like sigma is the standard deviation. If you take it bigger, then it will just more spread. Um, and um, and compare with the box filter, if you remember, we have this simple box filter here. Is it 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 doesn't have this ringing artifact or like this. Yeah, I shouldn't say it's ringing because it's a horizontal and line artifact here, as you can see. And it's you don't have this artifact because if you remember, okay, if you remember like what we talked about like previously, that whenever you are doing like filtering or like convolution in the spatial domain, is correspond to like a multiplication in the frequency domain. So if you think of the box filter was the frequency domain response, it's like this. So therefore, like you have kind of like a little bit artificial like ups and down in the frequency domain here. Like so you cut off like some frequency like suddenly here, and then it get a little bit bigger here. And so this corresponds to the artifact basically. So and using Gaussian filter is kind of nice because it's also smooth in the frequency domain. Actually, you can easily show that like um the uh the the Fourier transform of the Gaussian distribution is also a Gaussian distribution. So basically you also get back this Gaussian form here, like this one here, if you apply Fourier transform to the filter itself. So then this is the Gaussian filter, basically. It looks better like visually as you see this again. And very simple. It is a low pass filter, right? Okay, actually I should ask you whether it's a low pass or high pass, but it's obvious, obvious, I guess. Um, so the next one I like to mention is the medium filters. It's very useful for salt and pepper noise. Oh, by the way, like maybe just a short question, like to see if you know like what's medium is. That's medium. Let me move to like here so I can draw something. So let's say if I have several numbers here. Let's say 1, 1, 1, 2, 2, 9 numbers here. Let's say 3, 4, 5, 6, 7. Let's say. So that's is that 9? Actually, I got 10. Maybe I made it 11. Maybe just make it 9. So like that's 9 numbers. So what's the median of this thing here? Oh, that's good. So you guys know median. So median, yeah, you know the median incomes as well, that kind of stuff, right? So basically, for example, if you compute the median income of a population, that would be like you sorted like the incomes of like entire population, and then you look at like so this is a population here, like people actually, maybe people is n here. Then you look at like what's the income of the n over 2 person. That will be your median. So in this case also, like you sorted the entire sample, you take the middle one, that gives you the median. And now, so I guess you can guess it. So for median filter, let's say if I have a patch here, maybe it's like, actually, like maybe I have 90. Actually, I already have it somewhere. Maybe I don't need to draw it. Like for example here, now I'm applying a median filter at this pixel, right? So taking this neighborhood, right? Yeah, sorry, I need to get back to the chat. What I'm doing? Let's see. Okay, now I can. The problem of moving desktop is like the chat didn't come with my desktop, so I cannot see your chat if I. So okay, what will be like the output of the median filter at this pixel here? So the neighborhood is here basically. I mean itself is 90 here. So what's the median value? Like if I apply a median filter. Yeah, yes, it would be just 90, right? If you sorted that out, that would be like 0, 0, 0, 0, 4, 0, and then 90, like all 90. So therefore, the one in the middle will be just the median. Yeah, so, okay. And yeah, here, yeah, okay, that will be, it's not showing here, but it should be 90. So, median filter, as I mentioned, it would be like very useful for this kind of like salt and pepper noise. So they call this salt and pepper noise because you have this basically white and like black pixel. Like basically you have like random pixel get either kind of like set to like 255 or set to 0. So if it's set to 0, you get black. So it's like pepper. If you set to 255, it's like white. It will be like salt. So and for this salt and pepper noise, if I just use a Gaussian filter, like use a box filter, let's say, a box filter doesn't do well. Like this is 5 box filter. And I have, let's say, another one here. Oops. This is a stronger box filter. Let's say I have 11 by 11. I just, I guess it's just blur the entire image. So, and wait. And I can, if I use median filter, it do very well actually. This is just median filter with like the kernel size is just 3 by 3. It's just like the one we show. So if we use 11 by 11, that will basically take the neighborhood of like that would be total 121 pixels, including itself. So you just get, yeah, it's not. But anyway, like still doing quite good, like compared to the box filter. So that's median filter. So one more filter I like to mention is like more recent, like this like box filter and like median filter, like Gaussian filter like has been around like for many decades. Like this one is like, if I remember correctly, either it's in it's still like a couple decades, I guess, like maybe like in 2000, around 2000 or like late 90s. So the bilateral filters, like basically it's like you want to have a filter that is kind of like adapt to the edges. So as you can see here, if I use Gaussian filter, I will get some kind of halo like around the edges. So, and if I use this bilateral filter, I don't have this artifact. So the idea here is that I want to have, if you think of like any kind of like filter, not including like medium filter, but just like the filter based on convolution, like I convolve with something that I basically doing a dot product of the neighborhood of the entire neighborhood, taken as a patch with the filter itself with a kernel. Then you can think of that for each pixel that contributing to the output will be depends on just the distance, or like just depend on the location of that pixel. Like for example, I look through this queue, like the neighborhood of this pixel P here. This will only depends on okay, in this case, actually, you even use just a Gaussian blur will be like symmetric, right? It just depend on the distance from the Q, from the pixel, from the pixel you want to filter with, the P here. So we also if we want to make it adapt to edges, so we cannot just care about the distance of Q from P, but we also want to look at if Q and P, if the intensity are far away, then most likely they correspond to different objects. So therefore, maybe I shouldn't give as much weight for Q, for this Q here to affect the outcome of P here. So this is exactly the idea for bilateral filter. Okay, it's around 90 something. So basically just add a extra scaling factor here that basically kind of this will just this weight here will diminish as the range of as the intensity, the difference of intensity of Q and P increases. So if this is Q and P is far away, for example, here, this guy here, these two, this is Q here, this P here. So if Q this is showing the intensity here. So if Q is far away from P, so then the effect of this Q here for the filter outcome of P here will be much smaller. So therefore, this will be basically artificially cut off. So as you can see here, this is for this region here is more or less original Gaussian filter, but for here you just because this is far away from the intensity of P here, so therefore this will be just cut off basically. So that's the very simple idea of bilateral filter, but the result turned out to be pretty good. So this is another example. You have the ordinary Gaussian kernel here, right? So, but if I filter here, actually this is already showing that if I have a patch here, then the entire so the filter is more or less, because this is smooth, right? The filter kernel is more or less like the original Gaussian filter. But if I have an edge here, so this intensity here is very far away from the center pixel here. So therefore, this part is just cut off. So this, you see, is this is just cut off. So, and this is just another example. So, and this is a result using bilateral filter, you get quite a bit better, basically, than Gaussian filter. So, as you guys are going to submit your project proposal, I guess I'll just also mention a couple of project that we have done with some company before, and maybe you can take that as some idea that what you can do, what you may do. This is all quite doable. It's not a complicated project. Especially if you open Theorem, just take a couple packages. So for example, this is just a simple face recognition project that you have a camera like at the corridor, and then like people moving in, and then like trying to recognize the people person. So of course, like here, like if you're trying to implement from scratch, there will be quite a lot of work, but you can easily find like uh, packages that can do face recognition. Or of course, you can do from scratch as well, but it would depends on like, for example, like if you try to look for packages and then implement something, then I would expect you have something like more linear completion, right? Something like more linear appear to be like a final product that can be used say for somewhere, like I don't know. Uh, for example, like I this year, because I say all remote lecture, but I used to have like a um, face recognition app just to take attendance. So for example, like if you implement something like that, that's okay. So the core, even though the core computer vision part is not well, okay. I got a private message that cannot open my camera. I can come back to you because I maybe after the class. Um, so so yeah, where was I? Okay, yes. As I said, like if you use some open source package, let's say, to wrap up the entire application, that's fine. So, but then you should create something like near more like near a final product. But on the other hand, if you want to just implement something from scratch, for example, let's just implement face detection and then trying to after you detect the face, and then like you're trying to use some, for example, just simple PCA. We'll talk about PCA like, later on. So simple using like PCA that basically correspond to icon face and to decompose the faces and then do classification, train SVM and so on. That's fine as well. So then in that case, if you work like this, yeah, you can build a team. So, but as I mentioned, like preferably like not more than 3. So I have a discount policy there that if you have I remember it's a I forgot like, but anyway like the discount is exponentially increased. So for example, like if you have like 3 members, like you have 5% discount, but like 4 members you have 10% discount. I mean, if you have like yeah, and then 20 and so on and so forth. So because it doesn't make sense if you say like I have 8 person working on that, even though like I guess it's not likely. So 2 is a good number actually. I think 2 is a good number. You guys can pair up, I guess. And this is one example. This is another like simple example. Like that is like actually even more easy to implement. This one we implement from scratch. So it's just an overhead like people counter. So you have a overhead camera like at the door. Then like when people pass by, like pass the door, you can count the person, count how many people pass by. So you can, in this case, you know exactly the background, right? You can do some background subtraction because like the background is not likely to change. You can do a moving average, say moving average of the background, and then like you just like subtract the background. You know, like okay, this is someone's like pass by. Then you try to track that. Then whenever like it pass that, you get some. I mean, it's for example, if you do something like that, it doesn't know. It is okay. Like it doesn't have a very perfect counter. For example, like you after you finish that, you probably want to do some testing as well. Like let's say if you have accuracy 70%, that's fine. Like but yeah, but at least you try to build something. This is another like kind of like I guess more I would say like to me is a more interesting one. I don't know exactly what how people I don't think it's called summarization. I forgot like, but we call it summarization. The idea is that you have a video video stream like people coming in and out, and yeah, okay, is that running? I don't know why it's not running. Okay, so I don't know for some reason it's not running. Yeah, I guess I copy paste like from somewhere else, and then now it's not running. This is okay. So let's see if I can run here. Okay, that's bad. I shouldn't copy paste from somewhere else, and then it's not running now. So yeah, basically, like, why I have like some people coming in, and then we try to detect the person, and then we also record the time, and then we merge all the basically let's see if let me just take a quick look if I can. Wait a sec. Oops, what's my terminal here? It just disappeared. Uh, this presentation frequency. Wait a sec. Let's. It may be. Let's see if like the. I'll see if like my site is down or something. I think it's not. Okay, it's not down for the moment. Okay. Try frequency.ppx. Oh, I didn't. I forgot to change the. Okay. Let me update the link like afterwards. So, but let me see if I can pull back that video. Oh, actually, what one thing I can do, I can just do some quick fix here, and then okay. Yeah, I forgot to update the name. Let's see. Let's see. I have. Yeah, I think I can run it like that. Let me see if I can. Okay, now it's running. So so here is an example that like, okay, I have just say some people walking around like in this lobby here, like of the company, and then so you see there's a timer here. So this is actually the time that like the person actually passed that pace here. So they pass at different time, as you can see here. So this is like merging all this together. For example, like if you have video that's like 24 hours, and you want to watch the entire thing. For example, security need to watch the entire thing, but you probably don't want to like most of the time there's nothing happening, right? So you just want to put the important instance together. So in this case, I will just feels like all these instance together have with these people like this is a little bit more elaborate than the previous two projects, but you can imagine lots of like interesting kind of like idea like along this kind of line, for example. So okay, that's basically it. So I will go back to the stuff that I like to talk about today, is like resampling. So to start with, like basically, like I think like many of you should came across this before, so it's not something that maybe new for many of you, because this is just what I'm saying. Like if you have taken a class, like for example in cell processing or digital image processing, you always came across to trying to like scale the image, like resize the image, like make it bigger or like make it smaller. So let's say here in this case we're trying to make it smaller. So so the most trivial like or naive way to do it is just like downsample directly, meaning that like I will kind of remove some intermediate samples. Like for example, like for any samples in the middle, like for example, if I downsample like by 4 times, then I would just say only take one sample every 4 samples, basically. Like every 4 pixels, horizontally I take 1 pixel, vertically also like every 4 pixel or take 1 pixel. So therefore, like I should say like every 16 pixel, I would take 1 pixel basically. So I will get like 1/4 of that, and I can continue to do that. Like this is 1/8 of that. But if I count upsample back, like to look at this, like 1/4 and 1/8 of this image, it doesn't look too good. It may be like acceptable to you, but it doesn't look too good, definitely. In some cases, it's even much, I don't know, weird. For example, like in this case, if we try to subsample it and we get it bigger, that's just like some weird artifact here. It's not supposed to be there. Like you cannot, I mean, think of like how we get something like this. Like just from seeing this here. And there's another example, like for synthetic images, like sometimes it's even getting worse. Like apparently this is supposed to be like tiles that extend to infinity, but here it just become like, I don't know, this is very weird. And this is another example here that like around this region, like it's supposed to be just a curl, like a swirl, like all the way down, but like here, like it just I think you can see that like it's like I don't know how to describe that, like some weird artifact also like happen. By the way, there's another like actually this thing is something like interesting to illustrate also, because like this is also like a illusion, a interesting illusion. For those I probably won't believe is that like the green and blue curl here is like the same thing. Actually, the same color. Like this look like it's green here. This look like it's blue here. But actually, they are same color. Yeah. Yeah. Actually, if you zoom it in, then it's a more it's clearer that they're actually same color. So this is another illustration. I've like start with 225 by 225 and I go down 120 with 16 by 16, 64, 64, 32 by 32. You see, like it suddenly become like this. So it's totally unacceptable. So why we will get this, something like this? So there's some also like this kind of effect, like you can see that like also like when you kind of like from videos, for example, like just take this one, like this is a kind of like interesting illustration. So this helicopter is able to fly without the rotor is like spinning. And so isn't that amazing? So and this one like the real here just like turn both backward and forward. Like I don't know whether you can see clearly. Like so, it just okay. Maybe I should go back a little bit. Like so, around here, I guess like it's spinning this direction, and then I'm spinning backward now for some reason. So why we will have like this kind of like phenomenon? So if you think of like basically this is a phenomenon that actually happen when we sample. Oh, actually, okay, I gave it out, but I'm okay. It's okay. I guess in case maybe it's just a flash, like you guys may not see it. Maybe just ask one question that is both a poll and also question. Like, do you guys know this kind of like technical the terminology this for this phenomenon? What's the technical terminology for this phenomenon? Yeah. That's aliasing. Yes. You should have came across that if you have taken like signal system or like digital signal processing or like image processing and so on. So the aliasing, like this is like another illustration. Okay, yeah. Again I forgot to pull down the chat menu here. This is chat window here. So it's kind of like okay. And anyway, so this is a very nice illustration. So with the wheel here, now if I turning forward, but if I sample, like let's say if I sample slowly, I have a wheel like this, I have a cross in the middle, right? Now turning forward here, like this is like the first zero frame here, the next frame I move to here, the next frame move to here, the next frame move to here, and so on and so forth, right? Now, but on the other hand, if I don't look at this dot, then what I visualize will be like this thing is moving back to here, right? And then moving back a bit more to be here, and then moving back even more to here, and moving back a bit more here, right? So like instead of like rotating clockwise, it just looks like it's like rotating and anti-clockwise in a counterclockwise in a at a slower a slightly slower speed. And this is another illustration. So it's like this is sinusoidal, supposed to be sinusoidal like this. But if our sampling rate is not sufficient, then we become another frequency, like it's another sinusoidal with like a lower frequency. So this is like, so for sufficient sampling, if you have taken like kind of signal processing, you know that like if your signal is like F max, like you need to sample like 2 F max to have sufficient sampling frequency. So if you don't know that, like it's not that big deal. Like it's good to remember that, but let me illustrate like if, from also like the signal processing perspective that that we learned before, like we know we last time we mentioned before. Okay, one thing is like we just mentioned that if you think of like time and frequency representation, if in the time representation or like spatial representation, if you do filtering, then in the frequency representation will correspond to a multiplication of the frequency representation. And remember the Fourier transform is like symmetric, right? So it's just multiplied by like an exponential something. So therefore it's totally symmetric. So therefore like if I do a convolution like in the frequency representation, or like if I do a multiplication in the time representation, it will correspond to a convolution in the frequency representation. So I will have something like this, right? So I will have something like this. So I have, if I do a kind of like multiplication in the spatial domain, then in the frequency domain, I will have a convolution. Now, let's say what's the effect of sampling? Let's say let's just like consider a simple case. I sample every one sample here. So this is like, I sample the first one, like the zero sample, and then like I drop this second sample, like the first sample, and then I sample the second one, and so on and so forth. So if I do a, so if I do such sampling, then it would be like just this signal, original signal. Like you see, like I have all this original signal is actually oscillating quite quickly, right? So back and forth, back and forth, back and forth. Actually, it's oscillating rather quickly, as you can see here. But it looks like I have a profile that is solely, okay, anyway, right? You see it's oscillating quickly. But if I sample, kind of like sample every one sample here, it will be like this one. I can use my pen, it's better way. This one is going to multiply with this one, right? It's different color. So then if I look at the frequency response of this one, is actually this guy here is just have like pretty high frequency oscillation here. Like the length of the signal is like 64, so it's like that's like basically 30 cycles per this signal here. So, and then like the frequency representation of this guy is actually is just equal to have like, I have a DC component here, I have like zero here, and also like have the highest frequency here. So therefore, like if I have these two multiplied together, we correspond to these two doing a convolution here. So that will get something like this. So it's like I have this signal. So you can imagine like this one. I want this. Yeah, I want this point here. Okay, or I should think of like for this. Okay, yeah, this will be correspond to the DC, right? So this one convolve with this guy here will get me like these two peak here, and then I have like the same signal convolve with this part here will get this one here. Now, if so of course, like this is like the signal at the original sampling rate here. After I just dropped that, I just set it to zero, but I didn't downsample yet. So when I downsample it, then it will just become like this, right? It's just totally smooth out. It would be like if I downsample it, I would just have like this part of the frequency would be like chop off, right? I would just like take this one and then expand to, now this is my the maximum frequency will be here. Like everywhere, like outside this here will be just chop off. So I get a frequency representation like this. It becomes like a much lower frequency, right, than the original. So the original frequency is around here, like, but the final frequency will be like just here. So this is aliasing. You should have like seen this before, but like this is just an explanation, like graphic explanation, I guess. So and so therefore, like we need to have sufficient sample.
Can I ask a question?
Yes.
About that explanation? Yes. In the frequency domain, the convolution of those two graphs, isn't it just multiplication?
No, it's not multiplication here. You mean in the frequency domain? Yeah, the frequency domain here is you mean on this side, like this convolve with this guy, is that
right?
Yes. Yeah.
So
yeah,
if it's multiplication, then for example, around the zero frequency. So the first graph is zero.
It's not multiplication, because you see here I have the peak here is like 32, right? Yeah, or like minus 31. I don't know what's the value here precisely. Maybe minus 32. And this is like zero, right? So everywhere else is zero. So if I just multiply these two, it just gets all zero basically. This is really a convolution, yeah. So think of like this signal. convolve with this just delta function at 0 here, we just get the original signal, right? Now then you convolve with something like delta, this is like x plus 30, something like that. Then you will just shift the signal by minus 30, right? So this will shift to minus 30 that you get this peak here. But notice because this signal is actually like in Fourier domain, I mean like here, it should be everything is periodic, like so you can think of like every let's see, like after here, like there should be another peak here somewhere. Like this, I guess. Yeah, I think it's like this. So when this this one is shifted by this guy here, then I may let's see, I'm not sure my.
Oh, I see. So you
Yes.
just
Okay.
convolve in the frequency domain and
Yes,
to
I am
find
convolving the frequency domain, yeah, because I am
and the
multiplying.
product of real image. I mean the product of in the real the time domain.
Yes, because
I
multiplying
see.
is
I
multiplying.
thought in the reverse. Yeah.
No. Yeah, this is exactly like what. Yeah. Yes.
I see.
Yes. Okay. So okay. So this is just another example that like for images like this one, if we sample here, we'll get a good sample. If we don't sample enough, then like yeah, another like illustrations. For example, like just this one is easy. If I downsample but back enough here, then I will just get like 4 black here, right? So originally I should have like black and white, yeah, black and white alternatively. But here I will just get all black. So okay, then of course what we want is that we don't want to downsample too much. Another alternative is like we should just avoid aliasing by simply actually I cannot draw here. I think I have copied this one here. Like so to avoid aliasing, I should just for example, if I have what I should show is I have wait a sec. When okay, maybe yeah, this is actually not extremely helpful, this figure. Yeah. So let me draw something like that again. So what's going on is like when we downsample, we will repeat, right? So we will repeat like this. So for example, I have this here, right? I have something like this. So this part is repeated here because it's convolving like with the signal that like this. I have another spike here and something like this. And so this will be corresponding to aliasing. So this actually, this part of signal go to the high pass. It's not supposed to be, or I should say like this high pass signal, like it's easier to think of like this high pass signal supposed to be high pass, right? Oh, sorry, no, I shouldn't say high pass. I should say high frequency signal get to the low frequency that is not supposed to be there. So to avoid that, like either we can like kind of like do not kind of sample like as heavily, so then like our kind of like our signal will be a little bit farther away. So like this one here. Or if we cannot be willing to downsample, then what we can do is that we just apply a filter first, right? We truncate this part. So this part is gone now. Then we can sample in a lower at a lower sampling rate and still kind of okay. So at least this part didn't go to the low frequency now. So this is like the idea. So so therefore like typically if we really need to downsample like a lot, like this case, like if we downsample need to do 16 by 16. So what we can do is like first do this. So first, like do a low pass on the signal before downsampling, so then we'll get like better result, and at least look more like the original than this one have like very weird artifact. So, and this is another example, like the original example, we have this. Well, actually, by the way, like unrelated question, just like test you guys are still around and understanding stuff. Like, so for this one, like let's see if I can write here. It's very difficult to write though. So for location here, let's see, maybe this is not a very good one. That's bad. I cannot do Control C. This is so bad. I don't know why they always. Okay, I can erase all. Okay. So compare with this and this. So the first one, let's say first one is A. This is so difficult to. I cannot use this to write actually. Okay, this is A. Okay, it's not IA, just A. This is B. So which one contain more high frequency component? High frequency. Yes, most of you get that. So okay, just like this is actually just it's not for this class, but for this lecture, but for the last lecture. So just check your understanding. Like what do we mean by high frequencies? Like if you have more oscillation, in this case, in terms of image, it will appear like edges. Then this will be like the high frequency components. This one have like more high frequency components than this one. So at least this guy this patch here looks smoother here. So okay, like and this one here, if you compare with like what we had earlier, it does look better, right? So so this is like these two, yeah, it's like visually better if you first do like filter and do before you do downsampling. So how about upsampling? So upsampling would be exact inverse, actually reverse operation. So I can do upsampling just by like repeating the pixel, but it will be like very much pixelated. It doesn't look good. So we can do interpolation, right? For example, like if I just say upsample, like we can try to interpolate like things in the middle there. And in terms of frequency representation, you can think of like what we are doing in upsampling will be exactly the reverse operation of downsampling. And for upsampling, for downsampling, we will just like have this frequency band here to be more packed together. Right? When we do upsampling, we just like get them more farther away. So, but like we start from here, if we just insert 0 here, the effect is actually like we're repeating like, okay, I'm not going to show it, but like it will be like very similar to like what we did. If we try to show that, it's very similar to what we did like earlier. We'll have like some like extra component here. Like actually the first thing I should say is like it will just like simply got extended. So or like also I should say extended, I'm sorry. The other one is it should get compressed. So like this Actually, if I can. Wait. Okay, pin screen was not working for a moment, but I guess now it's working. Yeah, for some reason, I don't know, it's like a little bit, I don't know what's running in the background. I already shut down everything. What I mean here is that like, when we do upsampling, what it does is like, this, remember, like this signal itself, like actually like, when in the frequency domain is like it's repeated signal because you are, if you remember the Fourier transform is something like that, right? Fn, let's say I have Fn here, and E, J, omega is the frequency, and N, let's say, and then therefore like you will get like signal repeated like for 2 pi, right? Because like N is an integer here, so this Fourier transform like F omega here is like repeated, like have a period of 2 pi basically. So this is basically extend forever. Like 4 pi is the same thing here, right? And then same thing here and so on. Now when you do kind of upsampling, basically insert like some zero in the middle, what's going on is that you're going to compress this entire thing, like move down here to like this, right? This guy here now move to here, this guy move to here, and I have the 4 pi one move to here and so on. And this part will be like artificial, right? This is actually due to the fact that like you have some zeros like doing upsampling, right? So you originally you have the signal, let's say I have the signal like this. So this is like 0, 1, 2, let's say. My upsample like this become 2 here, right? And this become 4 here, let's say. Then I pass some 0 here, right? This I have some 0 here, 0 here. And this part is, this artifact is because I have this 0 here. Now, if I remove this artifact, I can do a filtering here. Again, I can do a low pass here. Then this will get removed, then I will get a smooth signal, supposing like this. Actually, this will correspond to an ideal low, this ideal low pass filter will correspond to trying to like filter the original signal with a sync signal. But yeah, typically it's hard to use sync signal because like that you need to have a very accurate like if you are just like synchronize a bit off, then you get something totally wrong. So in practice, people won't use this. But you can have approximation of that. For example, like linear interpolation. If you just have a triangular filter, will correspond to linear interpolation, and you can also like a Gaussian filter that you have a Gaussian kind of interpolation here. So for images, like to extend from 1D to 2D, then you will have like a bilinear interpolation, basically from here extend to 2D here like this. And you can get a little bit better using this so-called bicubic, like this guy here. But we won't go into detail. So this is just a demonstration like from this original one to get bilinear and bicubic. Yeah. And so and this as I said, like this is actually basically just correspond to like we going to like upsample that, then apply a low pass filter. Now, therefore, like if we trying to resample like to arbitrary kind of like, for example, like fractional ratio, that one way we can do is like first upsample and then downsample. So we can upsample, like for example, if I want to like 3/4 of the original scale, then I can first like upsample by 3 times and then downsample by 4 times, right? And then know that like when do upsampling, we should do like low pass filter after the sampling, upsampling, and we do low downsampling. We should do like filter like before the downsampling. So therefore, actually, if we do like upsampling and downsampling together, like we can replace this two low pass filter with just low pass filter here. Oh, okay. So I hope I'm not catching COVID. I don't know. I'm kind of like, yeah, I don't know what happened if I do like, yeah, let's see. I'm not sure. I need to, yeah, hopefully we'll see about that like after 2 days or so. So anyway, this is the, just want to say something like different, like just an interesting application, not exact application related to like this filters, as like doing hybrid image, like, so, by the way, like for this one, like if you are here, actually you can, of course, you see a woman here, but if you go all the way back, actually, maybe if you're at home, you can try to like step back and see like what do you see here. When you step back like by 5 meters or something, I guess you probably see a Lincoln here. And this is an illustration of hybrid image. So, so you see Einstein here, but at the beginning you didn't see Einstein there. You see some famous woman, right? I don't know whether she's famous anymore, honestly, for your generation. So anyway, so why we have that? So we basically how we generate that is quite simple. So what we did is like we have two images. One image is like we keep the low pass component, the other image we keep the high pass component, and then we merge them together like this one here. So now when you close by the image, you see the high pass component. When you try to move away, let's see, I try to move away and see if I can see that. I don't think like it's, okay, you're supposed to see the low pass. That would be like the elephant in this case. And okay, this is just another illustration. So this is another one, like you have a cat person here. This one, oh, by the way, okay, maybe another question here. Which one is the high pass? The cat or the person here, the man here? For this hybrid image. Yes. And okay, why we have this illusion or like for our visual perception? So the simple explanation will be like because like our sensitivity of contrast actually depends on the spatial frequency. So I don't know what you see here. Like here, basically showing is like a plot that along the horizontal axis we have increased the spatial frequency. You see the lines are more packed together, and vertically we have decreasing contrast basically. So when further down here, like we have like higher contrast, and going up we get lower contrast. So so for me, like if you think of like, okay, where's the boundary? Where, okay, you can look at along this line here and try to see like where you cannot distinguish the line. For example, I roughly see something like a profile like this. I see something around here, and then I maybe here go up more, then go down a little bit, a little bit like this maybe. like a profile like this, something like. But this is maybe a little bit extreme. I don't know. I see more like this. I don't know. But in any case, we have like some peak somewhere, like for some spatial frequency, we are most sensitive. This corresponds to like certain frequency component at certain frequency. That would be like, if you can imagine, maybe like certain thickness of edges that would be most sensitive to us. And as we have the image move farther away, okay, this is another question. So if we have an image moving farther away, does the spatial frequency of the image perceived by you decrease or increase? Did I ask the question? Yeah. Yeah, let me repeat the question. So if let's say I have the image here, right? So I just see here like a back image here. So now I move back. I move farther away. And farther away, to me, as myself as an observer, now the spatial frequency, I mean, original the image, right? I have a kind of like, you can think of this is an image signal. I can compute the frequency component and so on, right? This original spatial frequency. And then after I move away here, so move away, the image right, becomes smaller, right? Now my spatial frequency should increase or decrease, meaning that like here, like I just draw 1D. Like I draw 1D will be like I have some frequency component, right? I don't know. And then like maybe my signal should be like this, like something like, okay, I have like some signal like have concentrate at some frequency here. This is F0 here. Now when I move farther away, spatially I move to some like the peak, move to some F1. So F1 should be bigger than equal to F0 or like bigger than F0, or in this case it will be increased, right? Or F1 should be smaller than F0, in this case it will be decreased. So most of you guys consider decrease. Let's see. Should be increased or decrease. I didn't prepare that, I'm thinking. So actually I think should be increased. Why everyone thinks it's decreased? Let's see. Yes, I think it's increased. Actually, it makes sense to be increased. So why is increased? It's like it become more packed more closer, right? Because like, for example, you have lines here. So for example, like if an image, you have two lines here that correspond to like oscillating, like this is like 0, 1, or think of like a pattern here. Like I say, I have like oscillation, right? Like this is like dark, this is dark, this is dark, this is bright, right? So I'm oscillating like at this rate, like something like at this rate, right? So now if I get farther away, getting smaller, right? Now it's like this. Now I actually oscillating a bit faster, right? So therefore, like it's actually the spatial frequency, like starting from here, this entire spectrum will move up. Actually, will move up like to like maybe I draw on the same figure here. We'll move up like that, right? To here. Let's say this F1. So what's the
Can I ask a
effect?
question?
Yes.
So I'm not sure, but if we move farther away,
Yes.
then those three lines looks like just a single, the thick lines.
Oh, okay. That
Is
depends.
it different?
Okay. But yes, to you, if you cannot distinguish that, right? But you can have the three lines to be farther away, right? So that you manage to, for example, here, If you move farther away, you still see here, right? Then this is apparent. This is like getting. If you get to so packed that you cannot distinguish that, then of course, yeah. But I assume that you have perfect eyesight, is able to distinguish arbitrary fine. Yeah.
I see.
That would depends. That is the defect of the sensor, but in general, like it will kind of like increase. Right? Yeah. So of course, if you, yeah. But then now, what was that? What do we have for our original this hybrid image? Say I have a hybrid image. Let's say I have this low pass component, right? Let's see where should I draw it? Like, I have a low pass component here. Let's say put here. This is low pass component. The original image, right? I have a high pass component here. Let's say. Now let's say from my whatever from my vision sensitivity, that I am more sensitive at this frequency here, right? At this spatial frequency here. Then when I see this original image, I see this component, I see this high pass component, right? But as I move back, what I get is like I will get, let me erase this. Okay. So as I move back, as I said, like this entire profile will move up, right? So this one maybe will move to here, right? And then this green one will move like even higher frequency, maybe here. Now then it becomes that like we'll be more sensitive in this part here, right? So therefore, like when we move away from the picture there, like we actually sense the low pass component instead of the high pass component. So therefore, like that had the effect that when we are closer to the image, we see the high pass component. When we're farther away, we see the low pass component, basically. So that's basically explaining like, oops, I need to pull the chat window like down. Okay, one last thing like to mention is like the pyramid. Actually, I am thinking this is probably your second homework, so I should quickly mention that. So the pyramid idea is just like we want to, it's used lots of applications. So basically, imagine one application is like, I want to detect a cat or detect a face, but you can have a photo, like have a face is like, have, or like have someone like is closer than the face is bigger, and it's like farther away, the face is like smaller. So we want to like process in multi-scale, multi-resolution. So what we can do is like, we can start with the original image, but generate multi-resolution copies, and then like we try to process them for each of the resolution. So then this is basically just doing downsampling, right? So then the downsample will be done just doing Gaussian filter, and then downsample, Gaussian filter, downsample, Gaussian, downsample, and so on and so forth. So that will be just a pyramid, right? You just form a, actually often people call it Gaussian pyramid if you use a Gaussian filter to downsample, to do the blurring. So this basically Gaussian pyramid where you downsample that, sorry, you blur that, and then downsample, blur that, downsample, and so on and so forth. This is the Gaussian pyramid. And I like to talk about the Laplace pyramid. The Laplace pyramid will be, okay, sorry, the Gaussian pyramid is basically this part. You save this part, the original image, and then like the lower resolution one, the further lower resolution one, and so on and so forth. And for the Laplace pyramid, instead of like saving the lower resolution directly, want to save the difference version of the consecutive like Gaussian pyramid. So more precisely, like I will form the pyramids. I downsample this one, right? Boolean downsample, Boolean downsample, Boolean downsample. I get the lowest resolution here. Now I have the lowest resolution. I can upsample this back, and then I try to like do a difference of this upsample version and also like this image, and I get the difference. And this will be a one of my one tier of my Laplace pyramid. And then I try to do it again. I get another level of the Laplace pyramid and so on. So note that like what doing this is like for the interesting part here is like my final Laplace pyramid contain the lowest resolution of the Gaussian pyramid and all the difference image. And note that like for the Laplace pyramid, for the Gaussian pyramid, like it's usually used for example, like application for classification here. I have I can process a multi different resolution, right? But for the Laplace pyramid here, like once I produce the Laplace pyramid, I can reconstruct the original image out of the Laplace pyramid here. So my construction will be simply, I have this image here, right? Then I upsample this image, upscale this image, then I will get an approximation. And when I add this back, I will get this upper level of my Gaussian pyramid, right? And this one, again, I will upsample it and add the difference here. This is stored like from the Laplace pyramid, and get this one, and so forth, and eventually get back the original image. Now, so then one interesting application like this is just implication is that I can do image blending or like composting by using the Laplace pyramid. Basically, I generate simply the procedure is I just generate a Laplace pyramid here for both images, like apple and orange. And then let's say I will combine these two pyramids, simply just merge them together. Like I have like here, like I have pyramid, like if I do a kind of like decompose the image into this Laplace pyramid, like if I do, let's say 3 levels, I have 4 images here, right? And then I also like for another image, I also have like 4 images here. Now I just like literally for each level of the pyramid, I'll take let's say apple like the image from the apple from the left and the image for the orange from the right, let's say. And for each level of the pyramid, I just merge them together, literally. And then afterward, I just reconstruct the image back using the pyramid. And then I will have a pretty nice blending here. This is I just obtained from OpenCV. Actually, I will ask you to kind of like do it as an exercise. Let's see. I'll just illustrate that. So this is an example here that did exactly the same thing. So I can change the level here. You see, like I change the level like from 4 to 5 here, 5 to 6, 7, 8. There's some artifact here. Like this is something like I think it's like some wandering problem from OpenCV, but like I actually this will be your homework too. It should be quite simple. Like, but I would like you to like instead of like take apple and orange, I just take a photo from you and your friend, and then like just do a composting image. Right? Maybe the left face is you, and then the right face is your friend, and then compose them together. And it's good. Like I'm thinking like maybe I give you a more extra credit to add this bar as well. Like this bar is like it's easy to do in like OpenCV. I will talk about like how to do it like next time maybe. And so you can like change the level of like number of level decomposition by just doing that. Actually, I have some also like let's see, legacy code that I use OpenCV to sorry, Octave to do that, or like MATLAB to do this. And I try to use let's see one. Why so slow anyway? Okay, here. Wait, is that the same one here? Okay. Oops. Okay, anyway, I'm over time. I guess I shouldn't kind of like continue. So yes, you just need to turn in screenshot. Yes, please put for the homework, please like make it PDF. It's much easier for us. So just like you can just copy the code into, move everything into Word. Like for example, like copy the code into Word and then I copy the image in the Word and then convert to PDF and submit that. Yeah. So I guess yes. You can just pin out the Jupyter loop. Okay. I don't know. You need to Google that. I guess if you can try to pin it out. I guess you can just pin out the Jupyter notebook, but make sure that yeah. Yes, that would be like 2 people. I definitely that would be okay. Let me just make sure I didn't miss any question. I don't get the question. Like, what's SS stand for? Like, took SS of the or screenshot of the code and the output. It's okay. Screenshot of the code. Yeah, that's fine. Yeah, but we will check you guys actually do the work, like not plagiarizing anyone. Hopefully, and so please make sure you do your own work, and make sure you include the entire code. Like, of course, you use packages, it's okay, but like, I mean, standard packages, I say like, but if you use some other code that somehow like on the web is like, for example, not installed by, just simply pit install something, you need to specify that, and probably you should include the code.